big picture that summarized all that thing that I was talking about. What was the big picture? I wanted to draw this diagram. We started with the plus minus q, square root of plus minus q. After you did the homework, did you figure out the rule for this plus minus q? Do you know when the formula, the mechanism will give you plus root 2, root q, or negative root q? It's a number of negative that pops out when you cut it in half, right? So you have q and q minus 1 of them in the list, and when you cut it, if it still remains even, and so on. That's what that determines. So then we think about the square root of this number, whether it's in FP or not. Then what do? We come up with a nice description, right? Nice description in terms of zeta, right? And then we try to push down that root plus minus q, along with, in that process, we hope that we obtain this condition, p mod q. This is where the reciprocity takes place. All right? Originally it was mod p, now it's in mod q. So this part, it gets technical to exactly how we're going to do that. But with the example of 7 and 5 and 3, there are small number of cases, you can actually do it by hand without thinking about in general what's happening here, right? That was the homework, and that's what we did last time. Does that make sense? And here's a field tower picture. We start with FP, and up there potentially bigger field. Maybe it's the same field and actually bigger field if the square root 2 doesn't exist. So it's indicating that it's potentially the bigger field up there, right? And all the way up there, what field is there? Everything is done in terms of this qth root of elements of order q, right? That's what zeta is. And in general, elements here look like a0 plus a1, and all the way up to a to the q minus 2, I wrote it, right? But you can still cut it down by q minus zeta to the q, so you can write it here, like this. In one version, I wrote q minus 2. Now I'm writing q minus 1 there, right? It doesn't matter. If you play with z to the q, every qth power is replaced with 1, then you can see it goes down to that level. If you play with smaller one, the defining polynomial, you go down to the smaller one. But there's no unique way to do that in here, but you can certainly write everything in terms of this way. And Gauss later on stick to this expression. It's not unique expression, but you can write down any elements in here in this form. If it's a higher power, cut down by zeta to the q equals 1. Make sense? And Frobenius action is that you raise everything to the pth power, right? Then it's going to raise everything to the pth power because of the freshman stream, right? The raising the pth power is no longer complicated here. It's just individual term. What happened to a0 if you raise a0 to the pth power? a0 is a coefficient, came from downstairs, right? So they don't change, right? Fermat's theorem. These coefficients are coming from FP. So they stay, right? But all the other powers of zeta, right? A to the q minus 1, zeta, and raise the p, right? And the coefficient is still coming from FP, so it stays. Only thing that is changing is this power part, and all the coefficient is not changing, right? That's the situation. That's the action we're doing. You raise to the pth power, and that's what we've been doing to the right-hand side of when you're doing the homework. Then what happened is that because of that, here's a mod p world. Now all of a sudden, if you look at it here, right there, p appeared in the exponents of zeta, right? So let me write down our map. Zeta, what's the order of zeta? In the setting was order q, right? Order q, elements of order q, and you could describe using this element of order q, you can describe root 2, root square root 9, square root q, right? So this one has order q, so how's the community diagram goes? Log of base what? Was base g before, now what is the generator of this power? zeta, so it's zeta here, right? And this one is a z mod something. Anybody like to go for this one? Is that q minus 1 or q? Exponent is treated as a 0 when it reaches what number? Q, right? That's a qth power, therefore it's a q. All right? Exponent, this is an exponent world. It becomes a 0 when it reaches q. So downward map, what do you think the downward map is? What are we doing to that zeta? What kind of action are we doing? Raising to what power? Pth power, exactly. Pth power, right? Frobenius automorphism, reciprocity action is happening. So what happened to the z mod q over here? What kind of map is it? The something times y, right? That exponent is actually just multiplied to the exponent world. It's p times y. Remember these? And this function is called f, and this function is called h. Good? And this, under this interpretation, we're putting this p into the coefficient world here, right? So this is where p is put to mod q world. Does that make sense? This is where p is put to mod q world. P raised to the pth, and p appeared in the mod q world. So that's the reciprocity taking the p mod q is taking place in here. All right? So under what condition on the p over there in the mod q pushes down on here and makes this square root of q plus minus square root of q belongs to fp or actually bigger? So that's the reciprocity picture. Does that make more sense than last time? Right? If you do this action p, it becomes mod p condition, mod q condition. That comes back in and here. Change the relationship. Q squared mod p is now p mod q. That's what's happening. It's interesting if you think about it. It was a homework problem to come up with this general description of, in general, is q. So let's see if you would have agreed. Hope you did this recently, not like 3 days ago and forgot about it. So here's a general situation and description in here, and this is where we are doing square root of plus minus q, right? That's what you end up at. Then we have 1 minus zeta squared, all that, right? You go up to some index, I'm going to call zeta to the L. Because it gets bulky, I just wanted to replace it with that. Who remembers the formula of L? How much, after you put the square root, how much is L is going to be? That's right. But you have to half it, right? You already put the square root. The whole thing is 1 through q minus 1, oil of q, so it's q minus 1, right? And then you halve it when you take the square root and do all that crazy pulling out thing, right? So this is q minus 1 was originally there, right? And we half it. Where does the half come from? Because we took the square root. The entire list is a 1 through q minus 1, but half of them we rewrote and put it on top of the first half of it. So in the square roots, you only see that much of it, right? And then you have exactly half of them, negative 1 is pulled out. Do you agree? Exactly half of negative 1 is pulled out. So how many are there? Exactly L of them. All of them is q minus 1, and half is q minus 1 over 2. Right? And then this was a difficult part. And I'm just going to write it, capital S is because it's bulky and difficult expression. So S is, what is S there? Okay? First thing you pull out is that negative L. Agree? And then negative L minus 1. If you go from all the way to the right, you pull out negative 1 and negative 2 and negative 3. Do you agree? All right. So, and I pull out negative there. So it's same as 1, 2, all the way up to what number? Up to L, right? Up to L. So I'm going to write it simply like this, up to L and K. That's one notation. When you manipulate, when you want to see what is happening in general, this type of symbolic treatment it's always sufficient. Make sense? All right. So I think I should do example in here. Make sure that we're on the same page. With example of q equals 11. This expression is independent of p, right? So what p is not important in here. So here we have q is, well, if you have it, let's just calculate L, right? L is 10 over 2, so it's 5 of them, right? So 1 through 10, half is 5. Does that make sense? All right. So when you pull out, you will pull out negative 1 5 times. Right? So negative 1 will appear in here. Negative square roots like this, right? And then we have 1 minus root zeta, 1 minus zeta squared, 1 minus z to the third, 1 minus z to the fourth. So let's not pull out. I changed the positive. I'm going to pull out later. So zeta to the fifth. We reached the half, right? How does the other half look like? Not 6, right? How do we write it? 1 minus zeta to the, instead of 6, how do we write it? Negative version, right? You subtract from 11. 6 is what in mod 11? This is happening in q, mod q, right? In exponent. So what is that equal to? Negative 5, correct? So negative 5 appears. Does that make sense? And then pattern is that it just goes down like this, all the way down to 1 minus zeta to the negative. Is that all right? So I didn't pull out anything, just wrote this exponent in a negative representation, because it's the same as mod 11 world. That's exactly what this commutative diagram is about. If you're looking at the numbers in the exponent and zeta, it's the same as mod 11 here. So instead of writing a 6, you can write negative 5. So I pull out the symmetry. Then what do we pull out here? All the negatives, right? How many of them are there negative? 5 of them. So instead I put it over there, right? Okay. Then we pulled out all that negative, and then it became magically like this. So I'm skipping that part. Does that make sense? Negative, and pull out the negative power, and then it cleans up like this. Would you believe that? Let's focus on what is piled up here. Okay? So every time when you change to that shape, we're pulling out zeta to the negative 5, zeta to the negative 4, all the way to zeta to the negative 1, right? So I'm collecting here. Negative 1 pulled out, right? Negative 2 pulled out. Exponential law is added to there. Negative 3 pulled out. Negative 4 and negative 5. Make sense? So that's what's gathered in front of it as a power of zeta. So that's what I wrote up here. Do you agree? I pulled out, I wrote the negative outside, and just look at the sum. That's exactly 1 through L sum that's piled up there. So that's the general formula right there. So 1 through half of q minus 1, and I have exactly that number of copy of, this is already gone to that side, right? So I was wrong about this part. I should not have this one, because I put that over there in the plus minus q already, right? If L is even number, and this is going to appear as a positive q, if L here is odd number, after you have it, it still remains an even odd, and then that determines it. And negative 1 is going to, this is the formula, right? That's not wrote it correctly. And another thing I did wrong in here, this is before you take the square root, right? Before you take the square root, and then it all becomes square, square, square. So this is the version before you take the square root. What happens if you take the square root to the exponent? You have to divide it by 2, right? But how do you divide it by 2 in mod q? Multiplicative inverse of 2 in mod q. We're dividing by 2 in square root. That's all happening in here. Square root 2, right? Yes. When you put the square root here, this square, that square, that square, they all become just 1. But this number has to be divided by 2, right? But we have a little bit of freedom in mod q. Even if it is not divisible by 5, although it is actually not divisible by 5, an odd number of, maybe this divisible by, no matter what that is, you can still divide it by 2, right? Why is that? Even if it is odd, I can still divide it by 2. Because it's happening in what world? Mod Q world. Q is odd prime. You can still divide it by 2, right? Multiplicative inverse of 2. So I will use a notation 2 inverse instead of 1/2. So it indicates the multiplicative inverse of 2 modulo Q, right? Here's an 11. So what is the right formula in here? I forgot to put that. I'm glad I didn't move on to the next part. A lot of things to be fixed in here. Negative, still there, right? S is the whole sum before you take the square root. When you take the square root, you have to multiply by half, an exponent. Multiplicative inverse of 2. So that's the right formula now. Correct? All right. So that's the formula. Let's remember that. How do you determine this one? Plus minus? That's exactly -1 raised to what power? How many negative did we pull out in this setting? L of them. Right. L of half of them, exactly. Half is exactly L. Whole thing is Q minus 1, half is L of them. So that's the formula for deciding Q there. All right? If this is even and Q is a 1 mod 4 and things like that. So that's the description. That's a general description we have. And we have a formula of S and L identified right next to it. All right. All right, let's focus on this one. Now, this is description. What is the next thing we do? We do reciprocity action, right? Reciprocity action. So here's the reciprocity action. So where's the action? What action are we doing to that part? Remember the action we're doing? Action is raising both sides to what power? Not pth power. P minus 1 power, right? So then magic happens. So here's square root plus minus q raised to q minus 1 power. P minus 1, not q minus 1. P minus 1, right? And then right-hand side raised to pth power, and negative is written underneath it, right? So why don't I write this entire thing in alpha? It's a bulky notation, right? So why don't I just write it as alpha? Is that all right? Alpha represents the whole thing. We went to the denominator. We practiced it. And pth power appeared in there. Zeta raised to -2 inverse p multiplied to that sum, right? Everything is raised to pth power. And first product is raised to pth power, right? Or the last product, what is the last product? Lth power, right? So I have p raised to power. Here I use a freshman's dream, that thing. That raising this binomial expression to pth power, usually you have p plus 1 terms, but they're all gone, just 1 and zeta to the pth, right? That's what's happening. That's where the freshman's dream happened. That's the action part. Where's the reciprocity part? P now appeared in what world? Exponent world, which is mod Q world. Now P lives in that world. That's what reciprocity action means, right? All right. So when you practice 3 and 5 and 7 in the homework, is that right? It all became that we have this solid expression showed up down there, and when you go through that, all that example, they magically all reappeared, right? And cancel, becoming 1 or -1. That's what happened. Is that right? Because left-hand side, let me first clean that one, and I'll take your question. P over 2 minus 2, right? Because of square root 2. So this one is always plus minus 1. This is the Euler criterion, right? Always plus minus 1. So this is always plus minus 1. There are millions of different ways that how this plus minus 1 can happen. But from that example, it looks like it's just like they reappeared in different order. They cancel, leaving out trace of -1 sometimes and sometimes never even, right? That seems like the observation. That's the situation right now. So if we have actually P here, if Q is 11, right? If Q is 11, then we're going to consider P 1 mod 11 case, 2 mod 11 case, all the way to 10 mod 11 case, right? And see what happens to that. In all of the cases, it turns out they all reappear in a certain order. The cancellation is not in a strange way, but they just reappear. You can see these all things cancel out. What's left is 1 or -1. You can verify this, right? All right. So from that motivation, is looking at is what could happen to this 1 minus zeta to the kth power. So here's the idea. Idea is that from our actual observation, here we're looking at 1 minus g to the kth power, and especially, what am I writing here? Again, show up, and again, let me organize myself a little bit. All right, so here's the thing that I should say here. So this one, let me write down. I already said what I wrote down in here, so let me just move on to the next part. So first, what we start with, the exponent here is a 1 through L. And then next thing we do here is we multiply P to 1 through L, right? So I'm going to focus on this set A, which is 1 through L, 1, 2, all the way to L. All right? So I collected only the exponent. So you can look at this A over here in this picture. So I'm going to go back and forth and here, writing down in a different color. So I have A here. Let me write down A. A lives in this Z mod Q world. Let's see if that makes sense. I collected the exponent, right? 1 through L. Those are the exponents, right? So that's the next thing. The next thing I do, and the B is the rest of the part. B is L plus 1 all the way up to what is the last number in this residue system, mod Q? Q minus 1, right? So together with A and B, we have this complete system in here. A union B. That makes the complete Z mod Q system. Does that make sense? All right. But we are only interested in what happened to this A part when you multiply by P this way, right? So let's look at this Frobenius reciprocity action. We had 1 through L in the exponent. Now we multiply by P there, right? So that's the same thing over here in this vertical map. We have 1 through L that appeared in this part A, right? And then we're multiplying everything by P, which was the same as raising everything by P power, right? So I'm going to write down this one is still written in A union B, right? What's A? A is 1 through L. B is L plus 1 through Q minus 1, the other half of it. And we are multiplying everything by P, right? And you can see some of them eventually land in to 1 through L again. You can imagine that P and Y eventually, as an integer, get bigger number and cut it down by mod Q, right? Then you have no idea where it's going to land in. It could land in A, it could land in B. Does that make sense? So there actually, if you look at example, there are two possibilities that one of them go in there, or the other one go in there. Okay? So I decided that this is too general, so I decided to go with an example. Right? Here's, what is our example? Q equals what? 11 is our example. So let's think about A. What's A here? Let me move slightly to the left so that I have more room here. And, all right. Let's look at Q equals 11. 1 through what number? 5, right? And the 6 through 10. That's the division. What you're looking at in the square roots of plus minus Q is you're only looking at 1 through 5, right? Now I chose an example as an example so that I can actually do that. P could be random, but in a reciprocity situation is already. So I looked at this situation. P is 7 mod Q. It doesn't matter what P is really. P was put into the exponent world. All that it matters is that what is this residue class mod Q, which is 11. So I chose 7. So we're actually multiplying. There's 7 there, right? So I'm going to multiply 7 to everything. So you can see if I multiply 1 to 7, that shows up in here, right? That 1 goes to there. If you multiply 2, it becomes 3. So I'm cheating in here. So 1 goes to 7, 2 goes to 3. So actually, I'm going to collect. How do I collect this one? The 1 goes to then, and 2 goes to 3 here, so I'm collecting like this. And 3 goes to 10. 3 times 7 here. This part here is exponents of 3. You multiply by P7 here. 3 times 21, modulo 11. That's 10. That's what I did. So the 1, 2, 3, 10. 10 is out. So the 4 times the 7, if you do that, it turns out it's a 6 after you do the mod. The last number is 5, right? So 5 times the 7, P is 7, what is it? 35, right? And 33 is a multiple of 11, so 2. So it actually, that lands in a 2 here. Only 1 goes to 7. Only 2 and 5 actually land in the first 5 number. Everything else actually went to between 6 and 10. So 2 of them went down there, and 3 of them go across it like that, right? Does that make sense? That's the situation. So if you look at this situation, Q is 11, and P is 7 mod 11, then if you multiply P and everywhere, you will see 2 and 3 shows up again, but the other 3 numbers actually bigger than 5, exponent is bigger than 5, right? All right. But what do you do about that bigger than 5 part? You flip that sign, right? If it is a 6, you go to negative 5. If it's a 7, it becomes a negative 4. That flipping and change the magnitude smaller and pulling out the negative thing again, right? So that number of things that goes to the more than half thing, that is denoted by mu by Gauss. Gauss counted it carefully. So you actually do that and count this number by mu, right? Let's remember that part. All right. So let's see what I'm writing it down. All right. Now we have this thing, and this was an example, so why don't I continue right below this example in here. So I want you to look at the situation where we're staring at this case is 1 minus z to the k, where k is greater than L. Why am I looking at this case? After you multiply P, originally we had only through 1 through L, but multiply P, that the P times whatever happened that it might be bigger than L, right? So this is a situation, so I'm supposing that K is greater than L. So what do we do about this guy? 1 minus, how do we rewrite that K into a smaller one? If I have, for example, in this case, let me write it over here, mod 11 case, if I have 6, and you're changing to negative 5, right? The same process is subtracting Q off. So let me write that down. K is there, so it's the same thing. Doesn't matter, any integer multiple of Q I added here, it's the same. Q is treated as a 0, right? So K and K minus Q is congruent mod Q. So this is okay. But K minus Q will have this effect. 6 minus 11 becomes negative 5, right? So that K minus Q, now you can see that because of the size, it's a smaller, it's a negative number. K is always less than its negative number. Its magnitude is because of that, it's smaller than L. So this one now really becomes 1 minus zeta to the Q minus K. So that's the flipping part. And I'm going to call that one. So let me go back and change this one. I realize it better to change this one to Y, because that's what we're playing with up there. And this is Y, and that's going to be Y. Is that right? So what is that new number that we're looking at here? That is supposed to be less than or equal to L, right? Less than equal to L. So rather than introducing the bulky and difficult notation, I decided to introduce this one, just Y prime. If you start with a Y, that, I'm going to change that to greater than 1. That is greater than L, then you can always flip the sign and change this number Y prime that is less than L, right? So then what is the next thing we do? You pull out that zeta to the negative Y prime, right? And that becomes a zeta to the Y prime and negative 1. Is that right? So then we have to flip the sign, so we have negative 1 pulled out. What is it? Just negative 1, and that's it. Zeta to the negative y prime, 1 minus zeta to the y prime. That's something that we've been doing with the actual numbers, right? All right. So that's the formula. Let me summarize it here. 1 minus zeta to the y is equal to negative 1 and zeta to the y prime. That's the kind of complementary version, mod 11, and 1 minus zeta to the y prime. Something that we've been doing earlier in this whole part. Okay? So I decided to call this this y going to the y prime appearing here as a function. So I just defined h prime of y to be y prime. It's just a notation, function notation. So let me say this again. We're looking at 1 minus zeta to the too big an exponent, and then we can pull out 1 minus zeta to the small enough exponent with this some factors out there. And this y relationship between y and y prime. What is a y prime? Anybody remember the formula y prime? Was a q minus y there, right? It's q minus y. So that's the formula. Okay? So here's a new notation I'd like to introduce in here. This whole thing, now suppose this is happening in vertical map here. We're looking at A and B division 1 through L and L plus 1 through Q minus 1. That's what this one is here, right? And we're multiplying everything by P there. Is that right? And then some of them will land in this part that is A, part coming into A. So I'm going to look at it here. This is, I hope you are familiar with this notation. H is this function multiplied by P. Let me go back in here. And there's H prime. It's different. H is this map, multiplying everything by P. That's H map, right? Okay? So HA represents everything you get out of multiplying this one P, mod Q, right? And then if I put intersection of A here, that would say that still lands in A. Does that make sense? You send it and still lands in an A. I'm going to call that one C1. These guys are good guys. Nothing has happened to that exponent. But some of them will over here and land in HA. This is everything you get, right? That land in outside, which must be B. Is that right? Must be B. So then some of them land in outside. The number itself here is greater than L. But if you do H prime, what was H prime? You take that number Y that's bigger than L and make it into smaller than L by subtracting it from Q number, right? Then if I do that additional action, that's going to come back into A world, right? And I do nothing to C. C1 in there, right? C1 just comes down here, and there was this number lie outside that L. Then I do additional action, H prime, right? Then it lands in here, C2. So I'm going to write down version of a C2 here. C2 is HA. You hit it, that happened to land in outside A. Then you acted one more thing, H prime, which is changed into complementary size. 6 becomes 5, not negative 5, right? 7 becomes 6, that thing. That 7 becomes 4. So that. And then it comes back in here. So we have C and C2. That's what's going to appear in the numerator. You have some of them exponent is small enough, but some of them are bigger here. But by pulling out that factor, that we pull out 1 minus zeta, that is small enough again. So we have collected with a possible overlap, small enough, was it big enough, but you transform it into a small enough exponent. Then when you do that, there's always this thing tagged in an extra factor you have to take care of. Okay? So C1 and C2 both are in the subset of A. Does that make sense? It came back to A. These, some of them went outside, but by hitting H prime, we came back to A. And I claim C1 and C2, they don't overlap. Wouldn't that be great? They don't overlap. And what happened? You have 1 minus zeta thing over there. Some of them went outside. As you pull out, you come back to the 1 minus zeta with a small exponent. If there's no overlap, that will complete the whole thing, right? That's the idea. All right. So I'll do this overlap pattern here. So let's think about proving this one. Suppose it does overlap. Proof by contradiction, right? Suppose it does overlap. So what does that mean? C, how do you get into C? You start with a something there. I'm going to call, let's say, y1, all right? So y1 and y2. So let's say y1 happen to land inside the A. What that means is that you multiply P to y1 and go to the positive least residue. It still happened less than L, right? And the other thing is that, okay, here's a P y2 that happened to go outside, right? If you look at multiply P and it got bigger, and modulo Q, it happened outside the L. That's the situation, right? And nothing happens to this guy because this already landed in P. So if this is overlapping, that means such that, what condition are we doing? Py, nothing happens to that landed in A, is equal to the number that landed in outside B and doing this extra action H prime, right? H prime, when you do that H prime to Py2, they become the same. That's what it means, the overlap, right? Does that make sense? Suppose that happened. Now, think about the formula of H prime. What H prime does is if it is bigger than L, then you flip to the smaller size. So what is it? Py1 is, what is the formula of the Py2 in there? What is the formula of H prime? What is H prime doing? H prime is if you have a number, then it's a Q minus Y prime, right? That's the formula. If you see this number, you subtract from that Q, then it's going to be the smaller version. If you're looking at the 6, subtract from 11, and you get the smaller version. See if that makes sense. What this H prime is doing, if it is too big, greater than L, and you subtract from Q, then it's going to come down to the small. And that's exactly what the map was. But this is all happening in mod what world? Mod Q world, right? This is all happening in mod Q world. That's one thing you can enter. Then you can ignore Q, right? Then what is the next part? So Py1 is congruent to negative Py2 mod Q. So that becomes on one side all plus, right? 0 mod Q. Is that all right? So what can you do about that P mod Q? And it's like multiplied. These are kind of equations. We want to figure out the relationship between y1 and y2, then P is kind of fixed. Linear, what is it called? Linear congruence equation. This is what it is, right? So what do? You look at the GCD of these two things, right? And what is the GCD between P and Q? Two distinct prime. 1, right? That GCD divides 0. Therefore, it has a solution. And even that, it has a multiplicative inverse of P, right? So you multiply that, then it disappears. And there's no GCD that you have to divide with this modulus. GCD is 1. So P disappearing. Does that make sense? Or you're looking at it as a finite field. Y1 plus Y2 is divisible by 0 mod Q. Yes? In this one in here is that this multiplicative inverse of P exists in mod Q because they're relatively prime. Excellent. Good? So I got rid of it by multiplying it. Now you got down in here. So Y1 and Y2 both came from where? They all came from A, that we started from A, and some of them landed in A, some of them landed in outside B, and came back, right? So y1 and y2 originally came from here. They're all positive number, less than or equal to L. Think about the possibility of y1 plus y2. Smallest numbers is 1, 1. So this is the worst case, right? What is the largest case you can think of? Both being LL, right? Right? So LL is a 2L, correct? What is 2L? L was a Q minus 1/2. So L copy was before copying in here, right? And we're saying this one is a 0 mod Q, and the numbers in between 2 and Q minus 1. There's no multiple of Q, right? It's, make sense? Contradiction. Did I pull out contradiction? Therefore, if you start from here, let's see, if you start from here, some of them landed in here, and we'll keep it that way. Some of them landed outside, right? But if you flip that number, which is what we're about to do, then you come back to that set A without overlapping anything that came from C1. But cardinality should match the number of things that we started matching. They all came back in here, no overlapping. So we see everything coming back. So let me write that down. And here, conclusion of this claim is that corollary is that C1 union C2, right? What is C1 union C2? C1 started from 1 through L, landed back in here after you multiply, and C2 fills the rest of the pot. So if you write this one in correct order, what would be the first element? 1, right? And 2, and 3, all the way up to L. Is that right? They all came back. We started with just half of the residues. They spread apart. As we do that process, you came back. So what is that process we were doing is, let me write down in this way. So here's another corollary. I'm focusing on that the product part, the 1 minus zeta part. So zeta y is here, then y is all coming from set A. Isn't that what was in the numerator, right? A was 1 through L, correct? A was 1 through L. And we see this much. And there's a zeta to the negative s complicated, but only focusing on this part in here. So, and then next thing is that we multiply this one by P, right? So after the action, and this is what you have. Okay? So, then the corollary is that what happens to this part is that there's some factor pulled out, but eventually we get everything back. Isn't that what it's trying to say? Right? Eventually get everything back. But in that process, I'm gonna prove it, but in that process in here, every time when you're looking at py that is too big, then you are changing into that right shape, but there's always this factor shows up, right? Okay, always this factor shows up. So every time when you have to flip that number, -1 shows up. So a certain number of -1 copy shows up. Do you agree? Whatever the number is, right? And then there's a zeta to the, what is that zeta? What number is it? Y prime there, right? So whatever that number shows up in there. So I'm going to fill that up later because it's complicated. But let me first give you the shape of this corollary so we can fill up later. All right, so we're going to figure out that power. Then we have to fill in this power, right? Make sense? You at least expect this shape of the corollary by flipping it. All right, so here's a proof of the statement that is unknown. right? So here's a proof. We start from y all coming from 1 through L and multiply p in there, right? So what I do next is that, what is it we do? Let me see, is that what I want? I wanted to split it into two parts, that this y thing that lands in on A times that thing that lands in outside A. That's A and B there. Let me continue here. Y that lands in there, so it's 1 minus py there, 1 minus zeta to the py in there. I didn't do anything except I split the product into two parts, right? That y that eventually, that's not the right notation, y that eventually goes to that, right? So that would be hy, y such that, sorry about this messy notation, but I hope you understand, y such that hy goes to, hy which is a py, so let me not use that complicated notation, such that py lands in where? ha a, right? Maybe that's good notation. And this part here, I'm collecting all the y's such that py lands in outside. I can split that group of y into two pieces, right? Then this one is exactly, these are, if you land it in there, that's exactly C1. So I can replace that with just y dummy variable, where y is coming from C1. I wrote this part as a C1 earlier, so that's a C1. And this part is not C2. C2 is not there yet. And this part here becomes y that is landing in HA intersection B, and that whole thing is this y. All right, I'm rewriting that py as a y, and that landed in here. So I'm replacing, you can choose a z to see this one's happening. All I'm doing is I'm replacing this py with y, so that's what this one is, right? And y is bigger than L. And this is not C2. What C2 was, we are right here, right? C2 is that if you flip that number, then it becomes a C2. That process in here is the following. I'll write down, I'm going to copy y, it's a C1 in here, 1 minus zeta to y. It became messy like this, so it's not relying on intuition of juggling with this partition of a set. Try to do this, more like algebraic. That's why it became messy. So I'm going to keep this one y like this, and then pull out this y to the negative part. And what happened to that is a negative 1. It's pulled out. I'm changing and going back to that formula was a z to the, what was that? Go back to the formula here. What's pulled out from y was y prime. This is the final formula, negative 1. Negative y prime is pulled out. Negative y prime and everything. The formula, if you go back, is a negative y prime, 1 minus z to the y prime in here. Right? 1 minus zeta to the y prime. Right? And y, and the relationship between y and y, so let me remind you of y prime is a q minus y. That if y is too big, and then you subtract from q, and that's what the formula was. All right? Then you can rewrite this one index in terms of y prime there. Here's a y equals c1. Y is coming from c1, 1 minus zeta to the y. And we're rewriting everything in terms of y prime. So you have to think about it a little bit carefully that if there's a one-to-one correspondence, but I'm just copying what's inside there and reindexing in terms of y prime, right? Y was originally up there in the intermediate part, and here, this is where y was coming from. But y prime is the same as you hitting with that h prime function. So y was there, y prime is in C2, right? So here's this one becomes y prime is coming from C2 this time. So you can rewrite it like this. C2 is the parts of a number that is less than L. So y prime is now a dummy variable. Then you can rewrite it over here. So you can switch this y prime to y there, right? So you have this one put together with this one. It makes a complete set, C1 union and C2, right? So your complete 1 through L shows up, except that this negative copies of this one and there, and copies of this y prime shows up in there. Then rest of the part is y is coming from the full set A, 1 minus zeta to the y. Okay? So how many copies of negative 1 is there? Gauss denoted by mu. That's exactly the number of elements that was came over here. The mu of them came over here, right? And then, of course, that when you send it back, it's a one-to-one map. So you have copies of mu there. And this part is messy. So let me finish up in here. I'll let you go. Negative 1, mu, and zeta to the negative of expression would be y is coming from C2, y, and the product. That was exactly copied in there. I hope you can see this. Negative 1 raised to muth power, and zeta is y prime. I forgot to put the sum in there, so it was wrong. You have to go back and change that negative sum of the y prime. And these old y primes are all different here. And when you pull it outside, the product goes to the exponent, and it becomes that. So that y, you can change the variable to y again, but they're all coming from the C2 in here, so you can change it into a summation notation. So write down C2 underneath it. Wrote down here again. So collecting all that C2. But so we don't have much information about what the C2 is, but at least we pulled out very nice shape in here that see clear cancellation with downstairs. Now if you put this one together with what we left out with this one, together magically it becomes 0 and becomes 1. That's a bit more calculation, but at least we saw that why this one cancels out completely. This, this part shows up exactly again, the full set A, and top and bottom, numerator and denominator cancel. All right?